Revealing quantum computing systems. Imagine a world where secrets are no longer safe behind locked doors. That's the potential future we're facing with quantum computing systems. These systems are like superpowered computers that can crack open encrypted information in minutes, unlocking everything from your online passwords to classified government files. But how does it work? And what does it mean for us? In this video, we're going to delve into the fascinating world of quantum computing, exploring its inner workings, its implications for data security, and its transformative potential for various industries. What is a quantum computer? A quantum computer is a highly advanced machine inspired by principles of quantum physics, which delve into behaviors of atoms and particles at the smallest scales. Unlike traditional computers or even supercomputers, quantum computers operate by studying and controlling the behavior of these particles in a fundamentally different manner. The roots of quantum computing can be tracked back to the early 1980s, a time when physicist Richard Feynman conceptualized the notion of a quantum computer designed to simulate quantum systems with greater efficiency compared to classical computers. Expanding upon Feynman's visionary ideas, subsequent progress was achieved by pioneers like Paul Benioff, Yuri Manin, and David Deutsch, who played pivotal roles in establishing the foundational principles of this emerging field. How does it work? To understand how quantum computers work, let's consider a simple analogy: flipping a coin. In a traditional computer, the coin's outcome, heads or tails, is represented as a bit, or either a 1 or a 0. However, a quantum computer goes beyond this binary representation. It can simultaneously consider both possibilities, heads and tails, as well as a mixture of both, such as a blend of 0 and 1, with varying proportions of each. This fluid possibility, akin to a mixture of lemon juice and water, where even a small amount of lemon juice cannot be disregarded, is made possible by the principles of superposition and entanglement in quantum physics. This unique property empowers quantum computers to perform operations at speeds vastly faster than traditional computers, while consuming only a fraction of the energy. This realization left Dave awestruck at the potential of quantum computers to revolutionize various fields, including security and healthcare. In the realm of security, quantum computers hold the promise of creating unbreakable encryption keys, making it challenging for malicious actors to intercept sensitive information. Major institutions like banks and companies are already exploring the use of quantum uncertainty for secure encryption. Moreover, in healthcare, quantum computers could revolutionize drug discovery and molecular research by efficiently studying the intricate properties of atoms and molecules. This capability opens doors to unprecedented advancements in medicine and pharmaceuticals. In essence, transformative potential of quantum computers extends far beyond traditional computing paradigms, promising to reshape various aspects of our lives, from security to healthcare and beyond. A game changer with far-reaching implications. In the realm of computer science, the long-awaited arrival of a fully functional quantum computer is akin to a monumental achievement comparable to the historic moon landings. This breakthrough marks the culmination of decades of dedicated hours of research and heralds the dawn of a new era in computing. For business, this emergence of quantum computing represents a gateway to immense wealth generation. Previously insurmountable challenges for classical computers can now be swiftly resolved, opening up new avenues for innovation and growth. Similarly, to scientists and laboratories worldwide, quantum computing promises to accelerate research endeavors, particularly in the quest for developing life-saving pharmaceuticals. The unprecedented computational power of quantum devices expedites complex simulations and analyses, facilitating breakthroughs that were once thought unattainable. Navigating quantum computing hurdles. However, despite the immense promise of quantum computing, several obstacles stand in the way of its widespread adoption. Quantum systems are highly susceptible to disturbances from the environment, leading to errors known as quantum decoherence. These errors compromise the integrity of quantum information stored in qubits, resulting in inaccuracies during calculations. To address these challenges, researchers are actively developing correction techniques and stable qubits. Quantum error correction involves redundantly encoding information across multiple qubits, enabling the detection and correction of errors. Additionally, efforts are underway to engineer fault-tolerant qubits that exhibit resilience against environmental noise and decoherence effects. Scalability poses another significant hurdle in quantum computing. Presently, quantum computers possess a limited number of qubits, typically numbering in the tens to hundreds. To tackle more complex computations and fully unlock the potential of quantum computing, researchers are exploring various technologies to scale up the number of qubits while preserving their coherence and reliability. Moreover, the encryption methods employed today to secure data transmission face a critical challenge when confronted with quantum computing capabilities. Classical computers struggle to solve intricate mathematical equations involved in encryption within a reasonable time frame. However, the introduction of quantum computing has potential to unravel encrypted data swiftly. At the heart of this challenge lies public key encryption, the cornerstone protocol for secure data transmission. In this system, individuals possess both public and private cryptography keys, generated by the same algorithm and interlinked. While the public key is used by senders to encrypt data, only the recipient possessing the corresponding private key can decode the message. This security of the system hinges on the computational complexity of deducing a person's private key from their public one, a task that entails immense computational effort due to the necessity of factoring large numbers. Quantum computing holds the promise of revolutionizing numerous industries, offering novel solutions to intricate problems and computations. Let's delve into some compelling applications poised to benefit from the distinctive capabilities of quantum computing. Cryptography. Let's start with cryptography. The impact of quantum computing on cryptography is profound. Currently, widely employed encryption methods such as RSA and epileptic curve cryptography rely on complexity of factoring large numbers for security. Quantum computers have the potential to efficiently solve these factoring problems, posing a significant challenge to existing encryption methods. However, quantum computing also opens the door to the development of new encryption algorithms resistant to quantum attacks, known as post-quantum cryptography. These advancements would ensure secure communications in the quantum era, offering robust protection against emerging threats. Optimization across diverse domains like logistics, supply chain management, and financial portfolio optimization. Optimization problems play a critical role. These problems entail finding the best possible solution from a vast array of choices, presenting formidable challenges for classical computers due to their complex nature. Quantum computing introduces a promising avenue for tackling these optimization challenges with unprecedented efficiency. Quantum algorithms, including Quantum Approximate Optimization Algorithm, or QAOA, and the Quantum Integer Programming, QIP, algorithm, hold the potential to revolutionize optimization landscape. By leveraging the principles of quantum mechanics, these algorithms can explore immense solution spaces more effectively than their classical computer counterparts. One such algorithm, QAOA, seeks to approximate the optimal solution by iteratively adjusting quantum parameters. This iterative approach allows for systematic exploration of potential solutions, leading to enhanced performance and faster convergence. Similarly, the Quantum Integer Program, QIP, algorithm addresses optimization problems with discrete variables, a common scenario in real-world applications. By harnessing the unique capabilities of quantum computing, QIP can efficiently navigate through large solution spaces, providing more accurate solutions in a fraction of the time required by classical methods. Drug discovery. Discovering new drugs is a complex and resource-intensive endeavor that demands substantial computational power. Quantum computing offers a promising solution to expedite this process by simulating molecular behavior and forecasting properties at unparalleled precision. In the drug discovery, quantum simulations play a pivotal role in exploring the potential of diverse drug candidates. By leveraging quantum computing, researchers can delve deeper into molecular structures, optimizing their designs, and enhancing the efficacy of treatments for a wide array of diseases. Through quantum simulation, scientists gain insights into the intricate interactions between molecules, paving the way for the development of novel therapeutics. This approach enables rapid screening of potential drug candidates, streamlining the drug discovery pipeline and accelerating the transition from laboratory research to clinical applications. Nanotechnology. At the forefront of scientific innovation, nanotechnology explores the manipulation of matter at the atomic and molecular scale to create materials with tailored properties. Fundamental to this endeavor is the ability to comprehend the intricate behavior of materials at the quantum level. Quantum computing emerges as a transformative tool in that pursuit. offering unparalleled precision in simulating quantum systems and unraveling the mysteries of material properties. Quantum simulations facilitated by quantum computing enable researchers to delve deeply into the underlying mechanisms governing material behavior. By gaining insights into atomic interactions and quantum phenomena, scientists can unlock the potential of novel materials with precise characteristics desired for various applications. This capability holds immense promise across diverse fields, from energy and electronics to healthcare and beyond. Quantum-inspired materials pave the way for groundbreaking advancements, ranging from more efficient energy storage solutions to ultra-sensitive sensors and advanced medical implants. Quantum supremacy and future prospects. In recent years, significant strides have been made in the pursuit of quantum supremacy, a milestone demonstrating a quantum computer's superiority over classical counterparts in specific tasks. In 2019, Google's quantum computer achieved this milestone by completing a calculation in just 200 seconds, a task that would have taken the world's fastest classical computer thousands of years to accomplish. This achievement underscored the remarkable computational capabilities of quantum systems. However, it's crucial to recognize that quantum supremacy represents merely the initial phase of a broader journey. The next stages involve augmenting the number of qubits and enhancing error correction mechanisms to address increasingly complex problems efficiently. Researchers envision a future where quantum computers transcend limitations of their classical counterparts, enabling breakthroughs in domains such as artificial intelligence, optimization, and climate modeling. This ongoing progression towards realizing the full potential of quantum computing heralds a paradigm shift in computer computational capabilities, offering unprecedented opportunities for innovation and advancement across various scientific and technological fronts. The global pursuit and cooperative ventures. Acknowledging the transformative potential of quantum computing, nations worldwide have committed significant resources to research and development initiatives. Countries including the United States, China, Canada, and various European nations have embarked on ambitious programs and funding endeavors to spearhead the quantum race. These endeavors are geared towards advancing cutting-edge quantum technologies, attracting top-tier talent, and fostering collaborations across academia, industry, and governmental sectors. Moreover, collaborative endeavors and knowledge exchange are pivotal in propelling advancements in quantum computing. Initiatives such as the IBM Quantum Network, the Microsoft Quantum Network, and academic institutions globally are forging partnerships and granting access to quantum hardware and software resources. Open source platforms like Qiskit, Microsoft Quantum Development Kit, and Forest by Rigetti are democratizing quantum programming, facilitating broader community engagement and accelerating the pace of innovation. What are your thoughts on potential quantum computing? How do you envision its impact on our world? Share your insights, questions, and ideas in the comments below. And don't forget to like, subscribe, and stay tuned for more exciting explorations into the frontiers of technology.